Hi, Nancy.
Hi, Shane.
So today, it turns out we're doing something a little bit different, right?
Little bit different.
A little bit different. You had a chance might be the wrong word, encounter with one of our...
a chance encounter with someone I sit like 20 feet
with
from.
one of our colleagues,
but, you know,
I'll let you go. Go ahead.
Yeah. So today Heather made some cookies. Heather, who is our editor-in-chief of EOS, so this is how it all started. Heather made some cookies. And so I was eating, my fourth chocolate chip cookie, and I started, just chatting with Heather, who I think I mentioned was the editor-in-chief of EOS, which is our news website and magazine. And I said, I have to go record podcast. Actually, I did a really interesting episode about plate tectonics. And Heather said, we have something coming out in the October issue of EOS all about plate tectonics. So I thought, let's bring Heather in.
I love this narration. This is
this is how it happened. So let's bring Heather in. Hi, Heather.
Hi, Nancy. Hi, Shane. Thanks for having me on.
Yeah. So explain to us what I guess you guys wrote about in the October issue of EOS.
That's right. The whole issue is about plate tectonics. So I was looking into some of the history, and AGU actually has a really interesting history with how the theory of plate tectonics developed. Turns out in 1967, Jason Morgan, scientist, he gave a presentation at the spring meeting, which of course we no longer have, of of AGU. And gave this presentation that kind of landed with not much excitement, right? People didn't really think much of it at the time. It was kind of weird. People didn't really know what he was talking about. He had measured some seafloor spreading, and people went on and did their own thing. Later, about a year later, his work was finally published in the AGU Journal of Geophysical Research, confirming the theory of plate tectonics. He had measured seafloor spreading, which showed that the continental drift was a real thing. And this would be very exciting, except he had kind of been beaten to the punch a few months earlier by two other scientists who had done their own research, published in Nature, and ta-da, plate tectonics was proved. Jason Morgan came along later. They're like, yeah, it's already been published in Nature. Sorry, guy. So that was kind of unfortunate. But it turns out Jason Morgan had published, he had made this outline for his presentation in 1967 that, of course, everybody had kind of thrown away. Like, do you keep your notes that you're taking at a meeting, right? And in 1990... so decades later, the scientist Xavier Le Pichon, he found his notes. And he was so excited about this that he said, Jason, I can prove that you came up with this feat first, that you had proved this first. And so he published a history of of all these events and what happened when in 1990 in another journal of tectonophysics, and kind of recredited Jason Morgan with proving this theory of plate tectonics.
That's fascinating. How did he find his notes?
He doesn't really say. I assume he was probably moving and was like found a box and, dug it up like we all do. Next to his photo albums.
No, that's really great. I'm excited. I love learning things.
Yeah, so actually, it's just so fortuitous that I interviewed Xavier Le Pichon, the finder of the notes. And also, himself, a huge contributor to the theory of plate tectonics at the EGU meeting in Vienna this past spring. So
great.
Yeah.
Welcome to the American Geophysical Union podcast about the scientists and the methods behind the science. These are the stories you won't read in the manuscript or hear in a lecture. I'm Shane Hanlon.
And I'm Nancy Bompey.
And this is Third Pod from the Sun, Centennial Edition. Well, that was fortuitous.
Yeah. So cool. But so it's great. So yeah, I interviewed Xavier at EGU, but just to go back, it's pretty crazy when you think about plate tectonics. So in 1960, we were already like on our way, to the space race was kind of underway. And scientists still didn't understand like why there were earthquakes and volcanoes where they were happening. They knew they happened, but why?
That's wild.
Isn't that crazy?
How do you not know that?
I know. Now that we're like, how do you not know that? Of course.
Right.
But so basically before there was this idea about plate tectonics, that there are these plates, basically, that Earth is made of these plates that actually move, they basically thought that Earth just cooled after it was formed, and as it was cooling, the planet's surface just wrinkled and contracted, and that's what made the mountains and all that stuff. So that's crazy.
It's like an old person.
So that's what they were kind of saying, and people knew though, like everyone looks at a map, they say South America fits together with Africa,
right.
and
like
that's
Pangea.
yeah. So back in like the early 1900s. Alfred Wegener had said there's this idea of continental drift, that everything was once one large continent and they drifted apart. But he couldn't really prove about why that happened.
Right.
So for a long time, people thought he was, they didn't
Just
believe
wrong.
him. Yeah, they didn't believe him. Wasn't well received. And it really wasn't until the 1960s that scientists discovered what actually was behind this all.
Yeah.
So, and Xavier, who I interviewed, he started his career just as this whole thing was starting to take place. And he was very involved with the discoveries that went along with it. But the interesting thing, just to start at the beginning, where we'll kind of start with his story, is that it really started about when they started studying the ocean floor.
Oh.
That's when it was not studying the land, but actually on the ocean, they saw that the ocean floor had these mountain ranges and these valleys, and they discovered these long ridges that we now know they call them the mid-ocean ridges that are these that are run down the middle of the ocean. And so that's when they really started to talk about what was going on.
Yeah, it's so interesting. I feel like that's a common thing in science when you're studying, or you think you're studying one thing, and then all of a sudden there's something else, right?
Right. And it wasn't really till I think after the World Wars, when they had a lot of this new technology, that they were able to see the ocean and understand what was going on. And just to note, when they're talking about the ocean, and Xavier is talking about the ocean, he's talking about the ocean floor, not the water part. Forget the water.
Right.
They're talking about the ocean floor, and when they're talking about the structure of the oceans. So
Very cool.
Yeah.
Let's listen.
My name is Xavier Le Pichon, and I'm involved with the Earth. And I've been for a long time because I started working in research 60 years ago exactly, in 59. In 59, I joined Lamont, now Lamont Geological Observatory. And I was going there to work on theoretical geophysics. And I had a Fulbright fellowship, and then the boss, who was Maurice Ewing, who was a very hard man, a typical Texan man, told me, look, I need a physical oceanographer technician on the Vema, my ship, which is leaving tomorrow. And then you can join the ship. You'll have a wonderful trip over the world. But I said, I came for theoretical geophysics. I said, that can wait, but you cannot wait to learn about the oceans. That's how it started. And that's a very exciting movement, because this was the time where I really decided to work on the structure of the ocean, because we were supposed to test whether there was a continuous mid-ocean ridge. There were earthquakes on that. And we knew where the earthquakes were, but we did not know whether any structure was associated with it. So with the ship, we had to cross the lines, and each time we were crossing and we were coming on top of the expected high mountains and valley in the center, we would have to send a telegram to Lamont and say, hey, Doc, you hit it again. So that was very exciting, because this was the first time that I discovered that our science could be predictive. Using the earthquakes, we did not know anything about what was below the water, but there were earthquakes. And then you associated it with something that we knew in the North Atlantic and say, you should find the same thing, and we found the same thing. So that was the beginning, and I was very interested in that.
So what was known at that time about mid-ocean ridges and about plate tectonics? What were kind of the theories that were at that time?
That was very interesting. At the time at Lamont, where there was this powerful man, Maurice Ewing, he had made his name by two things. He working with Frank Press, who later became president of the Academy of Sciences. And using seismology, they have discovered that the structure of the ocean was completely different from the structure of the continents. So it was clear that they had nothing to do with continent. All these people who transform ocean into continent by thinning or things like that did not work. There was a typical structure of the ocean, which the ocean was a world apart from continent. And from that, he deduced that continent and oceans were a permanent structure that could not be mixed. So continental drift was bullshit. Okay.
Okay.
That was basically his thing.
Uh-huh.
And he wanted to discover the ocean, so he had these ships all the time at sea. And it was a very exciting thing. But at the same time, people were progressively discovering that something was fundamentally wrong about the permanency of ocean and continent. Because the ocean, there was so little sediments in it that it was obvious that they were not this big cemetery that had accumulated
over time.
all the erosion of the continent, There were less than 1/20th of what you would expect. And progressively it came very, very, very obvious that oceans were very young. So you had this big contradiction. Why are oceans about 20 times younger than continents if they are permanent? I mean, do they have a process where they renew each time, and what happened? So there was this feeling that the ideas that were the substratum of our knowledge of the Earth, because the continental drift had been pushed aside as not compatible with geophysics, were crumbling down. That was fairly obvious. And then the second thing, when Ewing and Hazen imposed, in a sense, the fact that this new structure, which was 60,000 kilometers long, which was the mid-ocean ridge, they invented the term, in a sense, the mid-ocean ridge system. This huge system was the largest tectonic system at the surface of the Earth because there were earthquakes everywhere at the axis. And we had no place for this system in our understanding of the Earth. So what did we do about the largest tectonic system on the Earth that was completely outside anything we knew? So it's what's clear that these two facts, very young ocean, geologically young, of course, less than 200 million years old, and an ocean with an enormous structure which was worldwide, which was the largest on Earth, and that was completely ignored in all the schemes that had been proposed to explain the Earth. So clearly, something was fundamentally wrong. So everybody was desperately looking for something.
I feel like I can sympathize as a scientist. Well, I mean, I guess even like as a person, this idea that, this feeling, right? Like something's just off or not quite right, or something's wrong, but you have no idea what it is, or maybe
or sometimes something happens like on your car or something, and you're like, something is wrong, or like, I hear a noise, I don't know what it is.
It's like my partner's car right now, or like something's wrong with the transmission, and I honestly don't know if I want to know what's wrong with it.
Yeah, so it was an exciting time, I guess, the early 60s. They kind of were looking for these answers, like what was going on. And so first, in the early 60s, Harry Hess proposed that these mid-ocean ridges were where the hot magma was rising up to the Earth's surface from below the surface.
Okay.
So, and it was pushing the ocean floor away as it moved up.
Yeah.
And so this was the idea of seafloor spreading. This was the idea that it was, So then it's like this convection that happens, and then that renews the ocean floor. And then they're also discovering, with all this ocean research, that the rocks on the seafloor actually had these alternating bands of magnetism. And so what's happening is, as they're being pushed up from below the Earth, they're recording what the Earth's magnetic field is at that time. And over thousands and thousands of years, the Earth's magnetic field shifts. So when you see that it's changing, you can actually kind of date things and understand that, it hasn't been here all along. It's actually moved, So it wasn't a static thing. So they basically put these two ideas together, and they said, it's moving. The seafloor is spreading. It's moving. And its new oceanic crust is being generated at these mid-ocean ridges. That's like the newest stuff, is coming out of there. Does that make sense?
It does make sense.
Okay.
It does. I wish that the look on my face, I wish people could actually see us recording this, because Nancy's making these like gesticulations where she's like pushing her hands up towards the sky, like imagine like a volcano, what you would do with that's what she's doing. It's quite lovely. No, I get it.
Okay, no, good. No, because I hope it's all making sense, because I did a lot of research to try to understand it myself. Then later in the 60s, from all these discoveries, scientists solidified this idea of plate tectonics. And that's basically that the idea that the Earth is made up of these plates, and their movement is driven by the seafloor spreading. And at these points where the plates meet, whether they be continental plates or the oceanic plate and the continental plate, that's where we see earthquakes and volcanoes and other geologic formations. So it's all connected, going back to to why earthquakes and volcanoes are happening.
Very cool.
66, everybody adopted seafloor spreading. 68, everybody had adopted a plate tectonic in the sense of quantification of motions. So that was a very interesting time where you have this change of the complete infrastructure of earth sciences is crumbling down and it's being replaced. It's not that the facts have changed. The observations are the same, but the way to interpret them, they enter into something in which they can be really interpreted. So that was because we discovered the ocean. We discovered they had nothing to do with the continent, and we discovered that there was an active system, and actually the most active part of the Earth is below the ocean, not below the continent.
Right.
So that is basically the story, and it means that you have a time where before this begins to be realized, you were in the certainty, you knew everything. I remember after that, when I came to France and then I began to move around, I was quite young. I was 30 at the time. And suddenly I was, presenting these new ideas to old professors, not only in France, but in Japan, in Germany, in Soviet Union. They would tell me, but young man, what you say is completely stupid. You have ignored all the whole thing and so on. There was this very strong resistance. And this is why many of the new proponents were young. Because if you were older, all the things you had done, interpreted in the old frame, it was extremely painful to say, look, I have to change all that and interpret it in the new frame. I remember once Frank Press, who, I don't know if you had known him, but he was a famous geophysicist. He had been president of the Academy of Sciences. And I was in Moscow with him. That was when I was 30, and he had 35 years more than I was, probably. And we had a discussion about plate tectonics because I was giving a big lecture on plate tectonics at I don't remember what assembly of International Assembly. And in the preface of his most famous book, The Earth, he mentioned that there was this young geophysicist who began to aggress me. What were you doing? You old people, you knew all that, and why did not you do anything to discover that? And he was obviously he did not take it well.
Yeah.
No, okay. He did not mention my name, so, but I knew because I was there.
All right, well, I'm interested so there have been a lot of names thrown out, a lot of people who have been part of this process, a lot of contributions, but you talked to Xavier, what was his contribution?
But the other thing that I lived is you have the right theory and you discard it because you think that it doesn't fit the data. And that happened to me. That was the first thing. It was extremely painful. I had interpreted, I had a very important paper with Ewing and Langseth, two people from Lamont, on the interpretation, the amount of heat coming out of the mid-ocean ridges, on the heat flow. And I did really extraordinary innovative work. And that was published in 1966. And I produced the first quantitative model of plates. That is, including how it would produce, what heat it would produce, whether it would produce a progressive topography coming out of the ridges with a seafloor spreading model, because as the plate moves and becomes older, it cools down, so it becomes denser. So it because of the fact that it maintains the same temperature, it goes down and it produces a continuous slope. So I explained the slope is related to the rate of opening, and I computed it and I showed it, and it was right. And I explained that the crest of the ridge would come to such an amount, and I explained why, and everything was perfect, except that I measured the heat flow, and we had done a fantastic work on that. And I compared it to the theoretical heat flow that was produced by seafloor spreading. And the answer was we measured 3 times less heat coming out than there should be. And at the time, what we were measuring is the heat coming by conduction. The conduction is without matter moving.
Okay.
Okay? You heat below the table, if it's metal, for example, and you wait until the heat comes to the surface. It's only by transmission of the motion of the atoms and so on. But we had ignored convection. Convection is, for example, in the rocks, in the ridges, there is a lot of water in the cracks and so on. And the water circulates because it gets heated below by the magmatic material and so on, comes to the surface, goes out, and it takes a lot of heat. Actually, it takes more than 2/3 of the heat out. So the answer was that, but nobody knew that.
Oh, so it was losing the heat that would have explained it.
Yes,
Yeah.
you were losing this heat that could not be measured by conduction, and as a result, the measurements had no value. But that we will discover the answer to that only 10 years later, which was this convection. But then, to me, that meant it could not be that, because my computations were correct, our measurements were correct. I could not accept that. So I went to defend my PhD thesis in Strasbourg, in France, and that was my main conclusion: seafloor spreading is wrong. It doesn't fit. And I come back home in April 1966, and I discover this beautiful magnetic profile of Pittman that proved beyond doubt that seafloor spreading was there. And then I remember going back to my wives, at their house, and telling them, look, I just saw that, and my thesis is completely wrong. My conclusions are wrong, and I don't understand why. Everything was correct in what I did. And I was stunned. I had flying honors for my thesis and all that, but completely wrong. And it took me a horrible week to come around, and say. And the results say, I don't touch heat flow anymore. It's too dangerous, which is ridiculous. I should have taken that and immediately used it to produce it in the new system. And that was done by other people, Sclater and Franchetot from the West Coast. But the result is, then I moved to something else. And that's when I learned of what Jason Morgan had done, proposing to use spherical geometry to quantify the motion. And immediately I said, that's the thing to do. I want to do that full time now. So at Lamont, we were teamwork. You had to work together, you published together, you live together, you die together. Everything was done together, and under the boss. So I went to my other colleagues, very good people, Manik Talwa, Neil Long, and told them, do you want to work with me on that? They said, no, we have other things that are more important to do. So I worked alone. So during 4 months, I worked alone, and I published. I really did 3 things that had not been done before. First, I demonstrated that the Earth could not be in expansion. because there was a theory that there was only expansion in the ocean and no subduction. And I demonstrated with the new result that if this had been so, then the Earth would have inflated too much at the equator and not keep the shape that is necessary for a fluid planet turning in the... So that was out. It could not be expansion. And that was already something important. Then the second thing I did, I said, well, let's work on a world model. That is, I would predict the motion quantitatively everywhere, which had never been done. In the trenches of Japan, along the Himalaya, along the Alps. And I obtained all these things. And that was an enormous success. And it was immediately after used by the people of Lamont, Isaacs, Oliver, and Sykes, that used seismology and geology to show that produced a real new tectonics. They called it global tectonics. And then the third thing I did, which also was the first, I computed the first reconstruction of the Paleo-ocean, the old oceans. And that was very simple, that was finite kinematic. You just have to say, because now with the magnetic anomaly, we know the edge of the seafloor everywhere. So you just take the edge of the seafloor on each side of the ridge, and you put them back together, eliminating whatever is in between. And immediately you restore. And if it is correct, it should fit perfectly. See, and I did that for the first time.
Wow.
And I had decided by this time to go back to France because I had been offered to a job. And I produced with two colleagues the first book on plate tectonic would be the first manual of plate tectonic that I presented in Moscow at this meeting with Frank Press. And that became the Bible of the early people.
So at that time, when you all came out with that book, I mean, then was plate tectonics? I mean, was it settled? Was it this is what it is, or were still people?
Well, this is when the time where really the thing began to move. So this is the time where I would say from 68 to 73 or so, 72, plate tectonic began to structure itself. At the time, it was basically a theory of the surface of the Earth. We knew very little about what was happening in the mantle. And at the time, it was realized that plate boundaries that were within the ocean or between an ocean and a continent was well defined and relatively concentrated. But as soon as we moved into continents, for example, motion between India and Asia, things became much more complex. It was over a much wider area. And you came to this, I think, a second stage where we recognized that plate tectonics within the continents had to be described differently. We had to take into account wide areas of deformation in between two rigid parts. And that was well established with fairly good definition of what was happening by the 72, 73. And then we move into this continental area thing that had to be integrated. And then after, developments continued quite a lot. And in particular, a major development was the introduction of much better seismology and the introduction of GPS. Because one of the very important things that did plate tectonics, and this is the proof that it is a theory and not just an idea, is that it suddenly integrated discipline that were going their own way without exchanging. For example, the study of earthquakes was totally ignored in tectonics. You were making mountain belts, but you were not looking at the building factors, which were the earthquakes. The earthquakes are what building the mountain belt, but we did not know how to associate them. So seismologists and tectonicians were living in two different worlds. And suddenly with plate tectonics, they realized they had to live together.
I want to know from him, like, what is it like to be part of the person or part of a group of people who are at like the forefront of such an amazing discovery? Like, what
I
does
know,
that feel
it's
like?
crazy. It's like, I can't even imagine, you know? So what does it mean to you personally to have been so involved in this new theory, to be so intimately involved with really changing the world of geology?
Well, it was obviously an extraordinarily exciting time, you know. Also, I think it's obvious we were very fortunate. This doesn't happen every 10 years. So we were at the right time, at the right place. You know, that's we have to realize. Some of us benefited, some didn't know how to benefit as much, but clearly there was a benefit that was purely circumstantial. That's for sure. At the same time, it was an extraordinary time. I think it's something that you discover, and I discover more and more, is that the power we have to enter into what one can call the secrets of the earth, but you can call the universe or whatever. But that this world is not something unknown. It's somebody that you have to learn to discover, you know. I compare it in a way to the relationship in a couple, you know, and when you begin, you have no idea, you know, how it's going to react and what's going to happen and so on.
What do you think that whole experience can teach, you know, today? I mean, what can we learn from that for science-wise or otherwise, but scientists can take from that, perhaps?
Well, I mean, it's very well known that in science, predictions are most of the time completely wrong, because the prediction always are based on what we know, and science is constructed, but we discover that we did not know. So it's a very dangerous game. You know, again, it's exactly like for a couple. You know, you know something about the other person, but you know, it takes years to discover. I've been married to my wife for nearly 60 years now. It takes years to discover about the who she is really, and so it takes time. But my own feeling nowadays is that we are in a stage which is comparable to the 60s. That there is a big deal of confusion, but everybody is understanding that we cannot continue having plate tectonics being independent of the deep mantle. Clearly, there is a link. That's very clear now. But many things that we tried to do to put the link between the surface and the bottom obviously do not work well. Something is wrong, you know. And a conviction that we are going in this direction and we cannot tolerate anymore to say these are two worlds apart. They are not two worlds apart. But how do they link? And how did they link in the past? I think this is what we are living nowadays. So I think we enter into a theory that will be not plate tectonics anymore, but global Earth. And that will come in the few years to come. That is my feeling.
And what do you mean by that, by global Earth? What does that I mean, it's all more connected than we...
Global Earth means that it includes the contribution from all the deeper part of the Earth. You know, we used to in the beginning of plate tectonic, we used to only consider the upper mantle part, and even there, in not too well. Upper mantle, that's only 640 kilometers. You know, the Earth is nearly 6,000 something. It's a very small part. It's 1/10. And then nowadays we suddenly realize that what is on the core mantle boundary at the depth of 2,900 kilometers has an enormous influence on what happened at the surface. But it's not yet clear how this occurs.
Any, maybe your fondest memory of perhaps all these, I know it's been, you've been doing this for decades and decades, but is there one memory of being on the ocean or your work at Lamont with Ewing? I know you mentioned, is there something that stands out, like just a memory that you wanted to share or, something? Or
I have so many.
I know, that's why. I know.
This is one of the beautiful things about science, You can go any place in the world. Because you use a universal language, which is science, that everybody understands. Now, if I work in philosophy, I have a very difficult time with Chinese philosopher. So different. You have an adjustment, which is very different. The concepts are not the same. Even the idea of God, I think, are completely different. But in science, everybody talks the same language. It's restricted. And we eliminate everything which is not covered by our convention. But it's so powerful, you can work with anybody. I work in Japan, I work in Philippines, I work in the States, etc., etc. So you make wonderful friends who are of different cultures. So that's the other thing, especially me, I go in the field, and extraordinary. You meet the people, you make friends.
All right, folks. Well, that's all from Third Pod from the Sun. Thanks to you, Nancy, for bringing us this story.
Yes, you're welcome. And thanks to Xavier for sharing his work with us.
This podcast was produced by Nancy and mixed by Colin Warren.
We would love to hear your thoughts. Please rate and review us. Please write a review. Give us 5 stars if you love this podcast.
Yes.
And of course, you can always find new episodes wherever you get your podcasts or at thirdpodfromthesun.com.
And be on the lookout for more Centennial episodes to come.
As well as our regular episodes and from time to time special episodes.
Ooh, special ones.
Yeah.
All right, thanks all, and we'll see you next time.